Let's now prove that the triangle inequality for complex numbers, that the modulus of w plus z is less than or equal to the modulus of w plus the modulus of z. To see why this is called the triangle inequality, let's kind of draw what the picture looks like. Suppose that w is here. Well, that's a terrible point. Suppose that w is here and that z is over here. Then the complex number w plus z is found by basically the parallelogram rule for adding vectors. So here's the modulus of w. Here's the modulus of z. So if I draw a parallel w over here, then a parallel z over here, then that corner over there would be the point w plus z. And the point of this theorem is that the line in blue that I've drawn, that's the left-hand side, absolute value of w plus z. This green line here is the absolute value of w. And by symmetry, let me draw this in purple just to get a different color. If I draw this in purple here, then this line here has length absolute value of z, because it is basically a copy of the purple line that we see here. So it's a triangle, because it's a triangle, therefore the any one side has to be less than or equal to the sum of the other two sides. Okay, so let's prove this. That's the geometric proof. Let's do the full algebraic proof. Now, the proof of this depends very much on other properties about the arithmetic of complex numbers. So let's take a look first at the absolute value of w plus z quantity squared. We have previously proven that that is the same thing as w plus z times w conjugate plus z conjugate. Or, let's skip a step there, w plus z conjugate. We have also previously proven that w plus z whole thing conjugate is equal to w conjugate plus z conjugate. Okay, so let's multiply this together. We get w times w conjugate plus w times z conjugate plus z times w conjugate plus z times z conjugate. Okay, now the first part is w, absolute value w squared. The middle part here, let's see, this is going to be equal to w times z conjugate plus, now this other part here can be written as w times z conjugate whole thing conjugate. The reason that's true is because of our rule for multiplication. If I have a product conjugated, then now I get w conjugate times z conjugate conjugate. And if I take a complex number and conjugate it twice, I get the original number back. Plus, over here, I get absolute value of z squared. Okay, so here I have absolute value of w squared plus, now here I have a complex number, w times z conjugate, plus the same number conjugated. In other words, the part here that I'm going to circle in green and this part in green are the same. So those two things are the same, and we have a theorem that says that if I take a number plus this number conjugate, that's equal to 2. Well, change the color back to red. That's equal to 2 plus the real part of the number that was circled in green. So w z conjugate plus active value of z squared. Now we had another theorem that stated that the real part of a complex number is less than or equal to the absolute value of the complex number. So this is absolute value of w squared plus 2 times the absolute value of w times z conjugate plus absolute value of z squared. Now the next step, we have yet another theorem that says that the absolute value of a product of two complex numbers is the product of the two absolute values. So 2 times absolute value of w times the absolute value of z conjugate, like that, plus z conjugate squared. And so we have another theorem that says that the absolute value of z conjugate is equal to the absolute value of z. So that's equal to the absolute value of w squared plus 2 times the absolute value of w times the absolute value of z plus the absolute value of z squared. Now you notice this has the form a squared plus 2ab plus b squared, and so I can write this as the absolute value of w plus the absolute value of z squared. And so that's the end of the proof. If I take the square root of both the left-hand side and the right-hand side, I would have that the absolute value of w plus z is less than or equal to the absolute value of w plus the absolute value of z, and so that is the end of the proof.